You may have noticed that waves usually approach the coast at an angle, not straight on. The reason for this is that most waves are created by storm winds blowing far out at sea. If a storm occurred any place except here, say in one of these areas, then the waves created by the storm and traveling out from the storm area would approach the beach at an angle, not straight on, regardless of which way the beach is facing. Today, the waves are coming in from the northwest. Notice what happens to the waves when they enter the shallow coastal waters. They bend and tend to become parallel to the shoreline. But as you can see, the bending is not always complete. The waves pass through the surf zone at an angle and strike the beach face at an angle. Let's find out what effect waves like these have on a beach. First, let's find out what happens to the sand on the beach face, the exposed part of the slope. These red markers will show how the water moves. Let's watch the red markers again, this time tracing their movement along the beach face. The sand grains on the beach face must be following a similar path. What's happening to the sand on the part of the beach slope that's under deeper water in the surf zone? The waves passing overhead move the sand back and forth toward the shore and away from the shore. But are these the only directions in which the water is moving? Watch. The dye shows that the water is moving down the coast as well. Now we'll repeat the experiment, this time putting another spot of dye just outside the breaking waves. The second spot of dye shows that the water outside the breaking waves hardly moves at all, while the dye within the surf zone moves rapidly down coast. When the waves enter the surf zone, they break at an angle and cause this down-coast flow of water called a longshore current. Now let's see what this current does to the sand in the surf zone. The sand being moved onshore and offshore by the waves is also being moved down coast to the left by the longshore current. From the air, the pattern is clear. The waves approach the shore at an angle. Even though they bend somewhat, they strike the beach face at an angle. The sand on the beach face is carried in a series of arcs down the coast. In the surf zone, the sand grains are being moved not only back and forth, but also down the coast by the longshore current. Such movement of sand on the beach face and in the surf zone is called longshore transport. So we can think of the beach as a river of sand. The beach face is one bank of the river, the outer edge of the surf zone is the other. Much more sand is moved in the surf zone than along the beach face. These groins built along a nearby beach provide further proof of longshore transport. The sand has piled up on the same side of each barrier, thus showing the direction in which the sand is moving. Measurements of such accumulations of sand along both coasts of the United States show that the sand moves southward in most places most of the time. These figures show the number of cubic yards of sand that move south each year by these locations. Let's take a closer look at one of these places. We know the sand is moving down coast along this beach toward the harbor at Santa Barbara. Why does the beach appear to end here? And why has a sand spit over 300 yards long formed off the end of the breakwater? We can answer these questions by observing a model of the harbor in a wave tank. The waves strike the breakwater at an angle and bend around its end into the harbor. Now we'll add some sand and create a beach. Longshore transport carries the sand along the shore. The breakwater, acting as a dam, stops the sand, but only temporarily. When the sand reaches the end of the breakwater, the incoming waves carry the sand into the harbor. Once inside, the sand settles out in the quiet water behind the breakwater, and a spit is formed. Now we know that the sand flows underwater along the outside of the breakwater and feeds the spit. Let's watch this process once again. In time, the sand closes off the harbor. The problem at Santa Barbara is how to keep the harbor from being sealed off by accumulating sand. The solution is to take the sand out of the harbor and put it back into the natural longshore transport system. This is done with a dredge. The dredge digs up sand from the end of the spit at the rate of about 280,000 cubic yards per year, and it works the year round. The dredge picks up a mixture of sand and water here, pumps it through a pipe, and dumps it here. The sand spilled out onto the beach below the harbor flows down the beach toward the surf. Once the sand reaches the surf, it is picked up by the longshore current and is once again on its way down the coast. What happens when a dam is built across one of the rivers? The sand that would normally move downriver to the beaches is trapped. The reservoir has to be drained periodically and the accumulated sand removed. What would happen if all the rivers were blocked? Eventually, the beaches would disappear. So the rivers of sand that move along our coasts are actually parts of much larger systems. Whenever man interferes with such a system, he becomes involved in its operation. To the degree that man upsets the natural balance of the system, he and his machines must do the work that nature did before.